All right, hello everyone, and welcome to my channel. This is an educational channel, and we take a look at great theories of everything from the past, ancient and modern, and show you how to, or at least illustrate how these things can be used in the formation of a holistic worldview, paradigm shifting, awakening to 5D consciousness. And today is our 515th video that we've done on Dewey B. Larson and his reciprocal system of theory. And the reciprocal system of theory is a generalized theory of everything that's based on Larson's two fundamental postulates that he articulated back in 1959. And then he took those two postulates and derived a theoretical universe, what his universe would look like if his postulates were correct. And then he wrote some books where he compared his theoretical universe with the empirical measured universe of the modern scientists that they have compiled in their scientific tables. And we're looking at one of those books today called Basic Properties of Matter, where Larson arrives at equations for many of the basic properties of matter, such as the melting point, and then compares his results with the scientific tables. Now, if you want a fairly thorough rundown of how the reciprocal system operates, what its basic postulates, two fundamental postulates are, and what the ramifications are, you want to check out one of my first 474 videos that I've done on this subject, where I go into it in a little bit of detail. But for the purposes of today's video, I'm going to assume that you have a basic understanding. And if you don't, you can still hang on, and you might be able to glean some stuff out of this anyway, because Larson sometimes does explain himself in the text. But we're going to be reading, we're going to wrap up chapter 23 here, which is on charges in motion. And then we're going to start up with chapter 24, which is on isotopes. Okay, so start right here toward the end of chapter 23. The clarification of these numerical relations to put them in terms of natural units is a gigantic task, and it is still far from being complete. But enough progress has been made, particularly in the fundamental areas, to make it evident that there is no serious obstacle in the way of continued progress toward the ultimate goal. The special contribution of magnetism to the verification of these significant consequences of the postulates that define the universe of motion has been that because of its intermediate position between the one-dimensional and three-dimensional phenomena, it, in a sense, ties the whole fabric of scalar motion theory together. Recognition of this point early in the theoretical development led to deferring consideration of magnetism until after the relations in the other major physical areas were quite firmly established. As a result, the investigation of magnetic phenomena is not as far advanced, particularly in quantitative terms, as the theoretical development in most of the other areas that have been covered. There is another factor that has limited the extent of coverage, one that is related to the objective of the presentation. This work is not intended as a comprehensive treatise on physics. It is simply an account of the results thus far obtained by development of the consequences of the postulates that define the universe of motion. In this development, we are proceeding from the general principles expressed in the postulates toward their detailed applications. Meanwhile, the scientific community has been and is proceeding in the opposite direction, making observations and experiments and working inductively from these factual premises toward increasingly general principles and relations. Thus, the results of these two activities are moving toward each other. When the development of the reciprocal system of theory reaches the point in any field where it meets the results that have been obtained inductively from observation and measurement, and there is substantial agreement, it is not necessary to proceed further. Nothing would be gained by duplicating information that is already available in the scientific literature. Obviously, the validity of existing theory in any particular area is one of the principal factors that determine just how far the new development needs to be carried in that area. As it happens, however, the previous work in magnetism, and to some extent in electricity as well, has followed along lines that are very different from those that are defined for us by the concept of a universe of motion. And the results of that previous work are, to a large extent, expressed in language that is altogether foreign to the manner in which our findings must necessarily be stated. This makes it difficult to determine just where we reach the point beyond which we are in agreement with previously existing theory. Whether the clarification of the electric and magnetic relations in the special areas covered in the preceding pages will be sufficient, together with a translation of present-day theory into the appropriate language, to put electricity and magnetism on a sound theoretical footing, or whether some more radical reconstruction of theory will be required, is not definitely indicated as yet. Okay, that is the end of chapter 23 on charges in motion. And now it's time to start up on chapter 24, which has to do with isotopes. Chapter 24, Isotopes. While the magnetic charges involved in the phenomena that we recognize as magnetic all have the outward scalar direction, this does not mean that inward magnetic charges are non-existent. It is a result of the fact that the magnetic, two-dimensional, rotational displacement of material atoms is always inward. The principles governing the addition of motions, as set forth in Volume 1, require charges to oppose the basic motions of the atoms in order to form stable combinations. The only stable magnetic charge is therefore the outward charge. However, inward charges may also be produced under appropriate conditions, and may continue to exist if their subsequent separation from the rotational combinations is forcibly prevented. The events that take place during the beginning of the process of aggregation in the material environment were described in Volume 1. As brought out there, the decay of cosmic rays entering this environment produces a large number of massless neutrons, notated as M12 These are subject to disintegration into positrons, M0-0-1, and neutrinos, M-1/1/-1. Obviously, the presence of any such large concentration of particles of a particular type can be expected to have some kind of significant effect on the physical system. We have already examined a wide variety of phenomena resulting from the analogous excess of electrons in the material environment. The neutrino is more elusive, and there is very little direct experimental information available concerning this particle and its behavior. However, the development of the reciprocal system of theory has given us a theoretical explanation of the role of the neutrinos in physical phenomena, and we are now able to trace the course of events even where there are no empirical observations or data available for our guidance. We can logically conclude that in some environments, the neutrinos continue to exist in the uncharged condition in which they are originally formed, just as we find that the electron normally has no charge in the terrestrial environment. In this uncharged condition, the neutrino has a net displacement of 0. Thus, it is able to move freely in either space or time. Furthermore, it is not affected by gravitation or by electrical or magnetic forces, since it has neither mass nor charge. It therefore has no motion relative to the natural system of reference, which means that from the standpoint of a stationary system of reference, the neutrino produced at any given location move outward at unit speed in the same manner as radiation. Each material aggregate in the universe is therefore exposed to a continuing flux of neutrinos, which may be regarded as a special kind of radiation. Although the neutrino as a whole is neutral from the space-time standpoint, because the displacements of its separate motions add up to 0, it actually has effective displacements in both the electric and magnetic dimensions. It is therefore capable of taking either a magnetic or an electric charge. Probability considerations favor the primary two-dimensional motion, and the charge acquired by a neutrino is therefore magnetic. This charge opposes the magnetic rotation, and since the rotation is inward, the charge is directed outward. Inasmuch as this unit outward charge neutralizes the inward magnetic rotation, the only effective unbalanced unit of displacement of the charged neutrino is that of the inward negative rotation in the electric dimension. This charged neutrino is thus, in effect, a rotating unit of space, similar in this respect to the uncharged electron, and, as matters now stand, indistinguishable from it. As a unit of space, the charged neutrino is subject to the same limitations as the analogous uncharged electron. It can move freely through the time displacements of matter, but it is barred from passage through open space, since the relation of space to space is not motion. Any neutrino that acquires a charge while passing through matter is therefore trapped. Unlike the charged electron, it cannot escape from the material aggregate by acquiring a charge. It must lose its charge in order to reach the neutral condition in which it is capable of moving through space. This is difficult to accomplish, as the conditions within the aggregate are favorable to producing charges rather than destroying them. At first, the proportion of neutrons captured in passing through a newly formed material aggregate is probably small. But as the number of charged particles within the aggregate builds up, increasing what we may call the magnetic temperature, the tendency toward capture becomes greater. Being rotational in nature, the magnetic motion is not radiated away in the manner of the translational thermal motion, and the increase of the neutrino population is therefore a cumulative process. There will inevitably be some differences in the rate of buildup of this population by reason of local conditions, but in general, the older a material aggregate becomes, the higher its magnetic temperature rises. The charged neutrino, as a unit of space, is an addition to the space represented by the reference system, extension space, as we have called it. Where charged neutrinos are present, some of the atoms of matter exist for a time in the space of the neutrinos rather than in units of extension space or in the space of the uncharged electrons that, as we have seen previously, are also present. The charged neutrinos are rotating relative to the spatial reference system, and they are consequently rotating relative to the systems of motions that constitute the material atoms, systems that are defined relative to the reference system. The outward rotational vibration, or charge, of the spatial unit, the neutrino, is therefore equivalent to and interchangeable with an inward rotational vibration, or charge, of the time structure, the atom. When the neutrino and the atom subsequently separate, there is a finite probability that the charge will remain with the atom. The inward scalar motion of this two-dimensional atomic charge is the same as that of the two-dimensional atomic rotation. This fact that the rotational vibration of the atom induced by a magnetically charged neutrino is compatible with the basic magnetic inward rotation of the atom has a profound effect on the participation of this motion in physical processes. The ordinary magnetic charge is a foreign element in the material system, an outward motion in a system of inward motions. Magnetism therefore plays a detached role of relatively small importance in the local environment. The neutrino-induced rotational vibration or charge, on the one hand, adds to the net rotational displacement, the mass of the atom. And aside from being more dependent on conditions in the environment, is fully coordinate with the basic atomic rotation. Instead of being a distinct added motion, this induced charge modifies the magnitude of the previously existing atomic rotation. The presence of a concentration of charged neutrinos tending to produce inward rotational vibration of the atoms of an aggregate explains why an atom as a whole does not take an ordinary magnetic charge, and why these ordinary magnetic charges are confined to asymmetric atoms that have motion components which can vibrate independently of the main body. The outward motion cannot be initiated against the forces tending to produce inward motion. In view of the very significant difference in behavior between the inward charge induced by the neutrinos and the ordinary outward magnetic charge, we will not use the term magnetic charge in application to the rotational vibration of the type we are now considering. Instead, we will call this a gravitational charge, since the motion that constitutes this charge is a form of rotation and is compatible with the atomic rotation. It adds to the net rotational displacement of the atom. However, there is only one rotating system in the neutrino, whereas the atom is a double system. The mass corresponding to the unit of gravitational charge is thus only half that of the unit of rotation, or the unit of atomic number. For convenience, the smaller unit has been taken as the unit of atomic weight, or atomic mass. The primary atomic mass of a gravitationally charged atom is therefore 2Z plus G, where Z is the atomic number and G is the number of units of gravitational charge. In addition to the difference in the size of the units, the gravitational charge, or rotational vibration, also has a relation to the atomic structure in general that is somewhat different from that of the full rotations. We will therefore distinguish between the rotational mass of the basic atomic rotation and the mass due to the gravitational charge, which we will call vibrational mass. The relation between the gravitational charge and the atomic rotation will have further consideration from the standpoint of the atomic structure in chapters 25 and 26, and from the mass standpoint in chapter 27. Inasmuch as the gravitational charge is variable, the masses of the atoms of an element take different values, extending through a range that depends on the maximum size of the vibrational mass, G, under the prevailing conditions. The different states that each element can assume by reason of the variable gravitational charge are identified as isotopes of the elements, and the mass on the 2Z plus G basis is identified as the isotopic mass. As the elements occur naturally on the Earth, the various isotopes of each element are almost always in the same or nearly the same proportions. Each element therefore has an average isotopic mass, which is recognized as the atomic weight of that element. From the points brought out in the foregoing discussion, it is evident that the atomic weight thus defined is a reflection of the local neutrino concentration, the magnetic temperature as we have called it, and does not necessarily have the same value in a different environment. For reasons that will be explained in chapter 26, the transfer of magnetic ionization from neutrino to atom is irreversible under terrestrial conditions. However, there are processes to be described later that gradually transform the vibrational mass into rotational mass. At a low magnetic temperature, most of the single gravitational charges are removed from the system by these processes before a second charge can be added. As the magnetic temperature increases, the frequency of magnetic ionization of atoms likewise increases because of the larger number of contacts. As a result, double or multiple ionization occurs in some atoms. Each aggregate thus has a magnetic ionization level analogous to the level of electric ionization previously discussed. The degree of magnetic ionization of the individual elements depends not only on the magnetic temperature, but also on the relative ability of those elements to absorb the neutrinos. This is a property of the individual units of time displacement. The effective magnetic ionization, the number of gravitational charges that are added to the atomic motion, therefore depends on the atomic mass as well as on the magnetic temperature. From the nature of the addition process, we can deduce that at the unit ionization level, each net unit of rotational displacement should be capable of acquiring 1 unit of gravitational charge, half the size of the atomic mass unit, But the atom exists in the time region, whereas the neutrino is not subject to the factors that apply to motion inside unit space. The relation between the charge and the atomic rotation is therefore between mv, the vibrational mass, and mv squared. It says mr squared, the second power of the rotational mass. Furthermore, the atomic rotation in the time region is subject to the interregional ratio, which is 156.444. Denoting the magnetic ionization level as I, we then have the equilibrium relation. MV equals 1 I guess that's isotope. MV equals I times mr squared over the interregional ratio, 156.444. In this equation, the rotational mass, mr, is expressed in the double units of the atomic number, and the vibrational mass, mv, in the single units of atomic weight. The value of mv thus derived is the number of units of gravitational charge or mass that will normally be acquired by an atom of rotational mass mr if raised to the magnetic ionization level I. Okay, so that I is the magnetic ionization level. It is quite obvious from the available empirical information that the magnetic ionization level on the surface of the Earth is close to unity. A calculation for the element lead on the unit ionization basis to illustrate the application of the equation results in MV equals 43. So that is, lead is element 82. So it's basically 82 squared over 156.44. That equals 43 approximately. Adding the 164 atomic weight units of rotational mass corresponding to atomic number 82, we arrive at a theoretical atomic weight of 207. That's 82 plus 82 plus 43. The experimental value is 207.2 for lead. This close agreement is not quite as significant as it appears to be. Actually, there are stable isotopes of lead with isotopic masses ranging from 204 to 208. The explanation is that the value obtained from equation 24.1 is not necessarily the mass corresponding to the atomic weight, nor the isotopic mass of the most stable isotope. It is the center of a zone of isotopic stability. Because of the individual characteristics of the elements, the actual median of the stable isotopes and the measured atomic weight may be offset to some extent from the theoretical center of stability, but the deviation is generally small. In more than 60% of the first 92 elements, it is only one unit or none at all. Furthermore, the agreement is improving as more accurate measurements become available from experimental sources. In the nearly 30 years, since the publication of the first edition of this work, in which the comparative values were tabulated, the accepted atomic weight of 6 elements has been changed by a significant amount, and in all of those cases, the change has been in the direction of closer agreement with the theoretical values. Table 35 is an updated version of the original tabulation. The first column of the table gives the atomic number. The second column shows the value of MV calculated from equation 24.1. Column 3 is the theoretical equilibrium mass 2z plus g taken to the nearest unit, since the gravitational charge does not exist in fractional units. Column 4 is the observed atomic weight, also expressed in terms of the nearest integer, except where the excess is almost exactly 1/2 unit. Column 5 is the difference between the observed and calculated values. The transuranium elements are omitted, as these elements cannot have terrestrial atomic weights in the same sense in which that term is used in application to the stable elements. The width of the zone of stability is quite variable, ranging from 0 for technetium and promethium to a little over 10% of the rotational mass. The reasons for the individual differences in this respect are not yet clear. One of the interesting and probably significant points in this connection is that the odd-numbered elements generally have narrower stability limits than the even-numbered elements. This and other factors affecting atomic stability will be discussed in Chapter 26. Isotopes that are outside the zone of stability undergo spontaneous modifications that have the result of moving the atoms into the stable zone. The nature of these processes will be examined in the next chapter. In addition to the limitation on its width, the zone of isotopic stability also has an upper limit due to the restrictions on the total rotation of the atom. It was established in Volume 1 that the maximum effective magnetic rotational displacement is 4 units. The elements of rotational group 4b have magnetic rotational displacements 4-4. By adding rotation in the electric dimension, it is possible to build the total rotation up to 4-4